Hi, Arjun. Joseph.
Hey, sir.
Hello, sir.
Yeah.
Hi, sir.
Hi. How are things?
Good.
Good. You're
Yes.
comfortable with maths, Arjun?
Yes, sir. Yes, sir.
Yeah. What are these guys? Today I'm going to take only for 1 hour. I have some work. I thought two interesting topics I want to cover. So what I'm going to do is after this class, I want to have more sort of problems, practicals, and all that. So whatever we have learned so far, I want to consolidate it.
Yes, sir.
Okay, we'll wait for a couple of minutes. So I'm going to. So I want to get a feedback from you before people join. So what are the things you're finding it difficult? If there's anything which I can do.
Right now, sir, there is nothing as I think once the problem solving starts, we might find what's because this
Yeah.
is now theory, sir. So
No, theory is clear. No,
yes,
one
sir.
more theory we will take, then I'm going to stop. I'm going to do
Okay.
only problem solving.
Okay,
Okay.
sir. Yes.
So this is the last, last day, and since that last of the things, and then I'm going to do at least 3-4 classes. We'll solve problems. Sunday we'll have a class in the morning. And
Yes, sir.
okay. Arjun, what I suggest is that now have a look at. I sent you Vanilla's paper, right? She's in Chennai.
Yes, sir.
She's still looking for a house. She said she'll come. She said she's desperately looking for a house. She'll come also. So I sent you the paper, right?
Yes, sir.
Now, is it easier to read?
Yes, actually, the supplementary materials also the graphs that the table that they were flow chart that they put is also very helpful. So it gives a better idea.
Yeah. And also the equations. Now, do you find
Yes.
it easier to look at
Yes,
solve
sir.
the?
Yes.
Understand the.
After the compartmental model classes, I find it I can relate to whatever the equations and how they frame better.
Yeah, we will go slightly deeper into compartment models. So the thing is that I'm using compartment models to actually explain differential equations because
Yes.
it'll be easy for you guys to understand compartment models. See, uh, actually there are a lot of applications in physiology, okay, of mathematics, but they are at the second level. So I'm going to do some more intense things in other courses. Say, for example, next semester, uh, I'm going to offer this quantitative physiology. I'm going to do more maths, but with this maths, you will be able to follow that also, and you can attend that as well.
Yes, sir.
You may not be able to credit it, but at least you can understand it.
Yes.
It's easy to understand.
Yes, sir.
What happened? No one else? Did anyone join apart from you two guys?
I think people forgot maybe.
Yeah, that's what I think. I I think morning. Seriously, from morning we should send the
Link. Yeah.
link. Uh, it's actually slightly difficult concept today. So I'm waiting.
It always happens like this only. Like whenever you teach difficult, nobody would be there.
You two guys are there. You two guys are there. So okay. I'll just briefly explain it. Maybe go ahead in the next class to you know to more detailed things. I'll first. Dr. Shanti has joined. Very good. I think only Dr. Sundar is to join. Okay. So Dr. Shanti, what we are going to do is I'm going to do some theory today, and with this I'm going to stop. No more too much of serious theory, because we will go back and do revise everything and do a lot more problems. So you don't understand, we'll connect it and so on before we come back to some small amount of theory. Okay, so this is what I'm going to do. So I'm going to cover one more aspect, because see, we had done, I have to give more practical applications for what we called as eigenvalues and eigenvectors. Uh, uh, so eigenvalues and eigenvectors, I have to give some more practical applications. So I will do that. But before that, let us look at um, what is called as partial derivatives. Okay. Uh, Not a very, I wouldn't say very difficult concept, but it's an important concept uh, for you guys. So what do I mean by partial derivatives? Just a minute. I think it's just my, uh, there's no charge in my pen. It's okay. Yeah. So there are a number of functions which are uh, which are you know uh, which have more than one variable, independent variables. So far we have been seeing one independent variable. The function is a function of, say, t, or y is equal to some function of x, and so on. But we can also see that a function, say z, is a function of x and y. So what is a typical example for this? Let us look at body mass index. So B, which is the body mass index, let me call that as B, a function of the mass as well as the height. And this is given by a formula m by h squared. Okay, all of you know that. 64 kg, I'm 70 kg, 1.68 meters. You can interpret it. Okay, the question now is, with two variables, what we'll go to the graphs and other things on Sunday, but with two variables, how do I now take the slope? That's the question. So what is meant by the slope? So these are independent variables. A person can put on mass and his weight can be so much, and so on. So what is now being meant by derivative, or what is meant by slope? So now the slope is now, see, previously we were writing dB by dm, or dB by dh, and so on. So in other words, rate of variation of B with respect to h and m. Now both of them are variables, independent variables. So I'm going to write this as dou P. Look at the symbol, dou P by dou m, or dou B by dou h. So what does this mean? It means that what is dou B by dou, what is meant by dou B by dou m, which means that how much uh, the body mass index changes with respect to weight when h is a constant. Okay, h is a constant. So this is what it means. So, so in other words, when I differentiate it, I'm going to keep h as a constant. Let's understand this. So dou p by dou m. So what is the difference by d and dou? Dou means there is more than one variable. That's a partial derivative. D means there is only one variable, and I'm taking the slope of that variable. So dou b by dou m is equal to dou by dou m, okay, of b. What is b? B is m by h squared. M by h squared. Now, how do I differentiate it? I'm going to keep h squared a constant. I can take that out. Because at a particular h, how is the body mass index varying with respect to mass. This m of m dou by dou x of x or d by dx of x, same thing. What is d by dx of x?
1.
1. So dou by dou m of m?
1. 1 by square.
1. So this is equal to 1 by h squared. So dou b by dou m is 1 by h squared. So what does this mean? What does this mean? Suppose I am 1.68 meters. Let us say I am about 70 kg. Then dou b by dou m, okay, at 70 kg and 1.68 meters, dou what is equal to what? 1 by 1.68. So whole square, h squared. So what does this is about 0.3 something 35 kg per meter squared per kg. So what does this mean? Can you interpret this for me? What is the unit of P, by the way? Body mass index unit?
Kilogram per meter square.
Yeah, kg per meter squared. So now interpret this. Right.
If h remains a constant at 1.68 meters, for every kg increase in mass, the BMI will increase by 0.35 kilogram per meter.
Exactly. Brilliant. Absolutely brilliant. That's it. So what does it mean? It means that when someone is 1.68 meters, okay, and the rate at which if he puts on 1 kg, his body mass index will increase by 0.35. Exactly, right? So if it is, so you can see h squared, the way this is a very interesting thing. So if someone's height is 1.7 whole squared, then if he puts on 1 kg, his body mass index will be increasing to a much less. Let me calculate. 1.7 squared. How much is 1.7? So 2.1 by 2.89. How much is that? Anyone? Just getting my calculator. Anyone calculate it? 1 by 2.89. How much is that? 1 divided by 2.89. That's about 0.34. Right? Around 3.4.
Yeah.
So his increase will be less because it's 1 by h squared. So this is what is meant by partial derivative. Okay. Now, so can you tell me now how will dou b by dou h change? What is that? Dou by dou h of m by h squared. Can someone tell me this?
Minus 2m
minus
Yeah.
minus 2h cube.
2m by h cube.
Minus 2m by h cube.
2m by h cubed, because h power minus 2, when I differentiate it, minus 2 into h power minus 3. That's what this is, right? M is a constant, taking it out. So what does this mean? It's very interesting. So if for someone with a taller, okay, so the height variation between two people, the BMI varies by, okay, h cube, but it is at a particular point. You should understand that. So dou P by dou H, for me, 70, 1.68 is equal to minus 2 into 70 divided by 1.6, sorry, 1.68 cubed. Okay. So that would be, someone has a calculator. Two into 70 divided by 1.6. So it is around 29.5 minus 29.5. So what is this minus sign there? So unit is
Decreasing.
decreasing, m squared per m, right? So someone close to 1.68, or so it is, if he is taller, then body mass index for the same mass or same weight is lower by that amount. Of course, this 29.5 is only at 1.68, 1.68. Okay, with 70 kg. If it is something else, it will be different, isn't it? Suppose someone is 64 kg, minus 2 into 64 divided by 1.68 whole cube. So that will be minus 27 kg per meter squared per meter. So that will be depending upon that. So that is the, I would say, the partial derivative. Clear?
Yes, sir.
Any questions? Understood the meaning? Joseph, so you understood the meaning.
Yes, sir.
So this SARS has given us very interesting things. A lot of equations which have come out on SARS. Okay, after SARS on infectious diseases, right? So there's one of the equations which are spread of SARS after vaccination is an interesting equation. Okay, so equation is something like this: R naught. I'll explain this equation 1 minute. 1 minus V into D divided by 1 plus T, where R naught is the average number of new infections that each one can produce. You remember, people have been talking about this R naught value during SARS.
COVID also. Yeah.
Yeah, SARS COVID. You remember? People were
Yes,
all that time talking about R naught value. They wanted to reduce R naught to be less than minus 1, if you, less than 1, if you remember. And so the number of new infections that each infected person would produce this R naught value. So this is a typical equation that defines this. And D is the average. So we were in quarantine, or I mean, we had all the things. So D is the average number of days number of days an individual remains in the population. So if there is if there is no lockdown, he will be in the number of days will be more. If there's a lockdown, it will be less, and so on. Okay, right? Is that clear?
Yes, sir.
Okay. Let us say that. Let me take this to the next slide. Okay. Now, what are the things I can get from this? So the average is 4 days. Sorry, we have written there. Okay. Let's say that D is equal to 4. So D is equal to 4. Let's say that D is equal to 4. Okay. Average number of days individual remains in the population with infection. So let's say 4. Now, first thing I can get is the R naught value, initial days of lockdown, when there is no vaccination, okay, R naught value of 4, 0. V is equal to 0 because no vaccination. V is equal to 0. So that would be 5 into D4 by 5. So it's equal to 4. So what does it mean? It means that every individual can actually is free, is going out, can cause 4 other individuals to get infection. Clear? Okay. Now, let's go ahead with the fraction of population again. Suppose 0.5% of the 0.5, 50% of the population is infected. Then obviously R naught 4, 0.5 will be 5 into 0.5 into 4 by 5. So it will be 2. Right? Yeah. So that will be 2. So now, that's my equation. Now, what does dou R naught by dou D tell us? What is the meaning of this? What is the meaning of this?
Number of person a patient can infect depending on the number of days he's out in the population.
Exactly. So number of infections to the rate at which, to the number of days he can be there. He will be there in the population. Right. In other words, T being the average number of days an individual remains in the population. Okay. So let us calculate dou R naught by dou D. Okay. And then interpret this. Okay. Now, so in other words, let's put it like this: rate at which R naught will change for a change in D. That means, isn't it? So that's what is the correct change in D. Right? So what is this? I have to now differentiate dou by dou D of 5 into 1 minus V into D by 1 plus D. Right? Now, I'm taking that. What should I take out now? What is constant now?
5 into 1 minus V.
5 into 1 minus V into dou by dou D of
D
by 1 plus D. Right? So this is U by V. I don't know whether you remember this formula. U by V. So when
Quotient.
I have,
Quotient rule, yeah.
pardon?
Quotient rule.
Quotient rule, exactly, brilliant. So what is the quotient rule? D by dx,
U
sorry, of u by v,
U prime
v squared,
U prime
okay,
V minus
U prime V minus
v,
V prime U
v into u prime minus
minus U into V prime.
u into v prime. Exactly. So what is v squared in this case?
1 plus D
What
whole
is
square.
u and v? So this is u, this is v.
1 plus D whole square. A plus.
So quotient rule, that's what it gives. 1 plus d whole square.
Whole
See,
square.
if you don't remember this, simple, put ChatGPT, it will give you the value. That's all. Right? So v plus u is 1 plus d. Sorry, 1 plus d. What is u prime? 1
1
minus
D
d v
into
prime
1.
1.
1.
So what happens to that? So this becomes, this whole
1.
thing becomes 1.
Yes.
So this is 1. So 1 by 1 plus d whole square. Correct?
Yes.
So dou by dou r naught by dou d. Let me go back to that. At so, dou r naught by dou d at 4 comma 0, okay, is equal to 5 by 5 squared. When I put v is equal to 0, that's equal to 1 by 5. What does this mean now? That's what we interpreted. So now if you change d, the rate at which, if you introduce, say, for example, uh, some lockdown, okay, so the dou r naught by dou d would decline, because if you are going to reduce d, then the rate at which it is going to decline is 1 by 5 at 4. Suppose 4 goes to 5, the rate at which dou r naught by dou d is going to increase is 1 by 5. If you are going to decrease d, it is going to decrease by minus 1 by 5. That's the rate at which it will decrease. Clear? In both cases, we have put v is equal to 0. Right? I have put v is equal to 0. Now, what happens when I put vaccination? Let's see. Now, our friend Joseph has been working with AstraZeneca, right? So you
Yes, sir.
introduced so you want to justify, right? What? So you have not. So you are at this stage 4 comma 0. Now I'm going to say that, look, why not we introduce vaccination? Right? Okay. That means I'm going to calculate dou r naught by dou v. From the time when 0 vaccination is there, how is my vaccination going to change? Sorry, how is that my R naught going to change due to vaccination? So can someone give me an answer? So this is the one. So let me get that to the next page. So that's the equation. I have to know what is that I have to calculate? Dou R naught by dou V,
Dou V.
right? At 4 comma 0. No vaccination. So at 4 comma 0. So differentiate that.
So D by 1 plus D comes out.
right? 5 also.
Yes. 5 also, yeah.
Minus.
-1.
Minus 5d by
1 plus
1
D.
plus d. So with d is equal to 4, dou r naught by dou d is equal to -4. Josen has sold the vaccination. Just when there's no vaccination, even a small, we are talking about small vaccination. Sorry, V. A small vaccination. That's what it means. Dou V. Small vaccination. So at that point, the decline will be 4 at the rate of 4 new infection per unit increase in V. When there was no vaccination, okay, so what was happening? R naught was 4. And if you had introduced quarantine, there was a small decrease. Dou R naught by dou D is 1 by 5. But when you put vaccination, the negative is very high. And so it is -4. So this is the power of partial derivatives. Is that clear?
So when we are taking a small change in vaccination, if we can we apply V0? V has to be some positive numbers, right?
No. Okay. So what does this mean? Let us do this in just one-dimensional graph.
Yeah.
So let us say that we are now looking at V, okay, versus R naught.
Yes.
Right? For a given D, right?
Okay.
So which means that, what is this equation? D is equal to 4. Let's say D is equal to 4. So so the curve would look like, with respect to V, where is my equation? Yeah. So D is equal to 4 means 4 by 5 into 5. So that goes off. So this will be 4 into 1 minus V. Okay. 4 into 1 minus V. So so this will be the curve. 4 into 1 minus V. Right?
Yes.
So how will this graph look like at V is equal to 0? What is the value? It's 4.
Yes. Okay.
Right? And what is the slope of this graph?
-4.
Minus
-4.
4. And what is the type of graph?
Straight line.
Straight line.
Straight line. So that is -4. It's just because it's 1 minus V. 1 minus V squared means it would have been different. So what it means is, if it had been 1 minus V squared, the graph might have been like so. The graph might have been like this. That's it. So
Yes.
what it means is, this is the slope, or this slope, that's a constant. So we are finding out the slope at V is equal to 0. Clear?
Oh, yes, sir.
So we are finding out the slope. Okay.
Yes.
So this is the power of this. There are so many examples you can keep giving. This is the power of partial derivative. In fact, I'll take, after I finish some practical things, I will take some more examples and show you how this is useful. This is extremely useful. Sometimes what happens is, you will have more than see, these are explicit equations I have written. Say this R naught, this is an explicit equation. Explicitly, I'm saying R naught is equal to this much. Clear? But I may not have that luxury of writing it like that. my equation can be, many times this happens, that it is some function of x comma y comma z is equal to some constant, something like that it will be. Okay. In other words, it won't be easy for me to split, or I won't even be interested to split. So, for example, I will have x cubed plus y cubed plus z cubed plus some 8xyz is equal to c, something like that. You can keep writing that equation. Now, I want to know, z is actually my dependent variable and dependent variable, and x and y are my independent variable. Right? So how will I now write what are the two things, dou z by dou x and dou z by dou y? I may be interested in this too. So how will I write this? So we have seen this before, implicit equation. So I'll write it as, suppose I want this, I'm interested in this. Right? So I'll write dou by dou x of x cubed plus y cubed plus z cubed plus 8xyz is equal to dou by dou x of c. This is how I will write. Clear?
Yes.
So dou by dou x uh, of x cube, dou by dou x of x cube. What is it?
3x square
3x squared plus
y cube.
y cube. What will you have? Y cube is, y is an independent variable, I said.
So
0.
3y
Yeah.
square dy by dx.
I said independent. Doesn't
0.
depend on x. Pardon?
Which be it will be constant, right? We'll consider it as
Yeah. It's
Yeah.
like a constant.
So so 0.
0. Clear?
Yes.
Plus. Now, z is a function of x. I said it depends on x.
So because of the product rule,
Yeah, chain rule.
yeah, chain rule. So 3z
Z squared by
square dz by dx.
dz. Dou
Right?
Yes. Dou z by dx. X.
Dou z by dou x. Plus.
Plus
Now comes the interesting part. How are you going to do it?
8y
Product
comes
rule.
out.
8 comes out.
Y comes out.
Y comes out.
then product rule.
Product rule. X.
Yeah, x is at x is at.
X prime z plus z prime x.
So z into dou by dou x of
X
plus
x into
8
dou
is
by
there. Y goes with the 8 because that's a constant.
x
Then
into
X into dou
x into dou z by dou x. Dou z by dou x.
dou z by dou x because only z is there is equal to
0.
0. So 3x squared plus 3z squared into dou z by dou x plus 8yz into dou x by dou x is what?
1.
1 plus 8
8yx
into 1 8yx into dou z by dou x is equal to 0. Now I can find out what is dou z by dou x. Right?
Yes.
Just take it to the other side and do whatever. Same way you can do dou z by dou y.
Yes.
So this is implicit functions. So implicit differentiation. So what is that essentially we have done? Let's just put some mathematical thing to it. So I have had some function of x, y, z. Okay, and I want to differentiate it with respect to dou f by dou x. Is what? This is what. So essentially, what did I do? If you remember, if f is a function of x, Okay. So remember, what did we write? Dy by dx is equal to limit as delta x tends to 0, function of x plus delta x. Remember, this is what we did long time ago, divided by delta x. This is what we wrote as a
Yes.
definition for df by dx. Right?
Yes, sir.
Now, what is dou f by dou x? So dou f by dou x is limit as delta x tends to 0, function of x plus delta x, keeping y is at a constant, minus f of x, y, z divided by delta x. So the same thing, I'm keeping other guys constant. That's all. So I have now three variables, x, y, z. That's a function. Okay. So I have three, all of them are independent. So people write this in various ways. So people sometimes write this as dou f by dou x. People write it as f, this x comes here, f x. So this means this is written like that. Clear?
Yes, sir.
So it's written like that. Sometimes what you will do is we can find out dou f by dou x. Okay. And then that function what I got can be differentiated with respect to dou y. Or dou f by dou y. And then that function I will differentiate it with x. So this becomes f yx. Actually, you can show that is equal to f xy. So I can, this also I can do. Clear? I can do that. Actually, higher derivatives play a very important role. So what is higher derivative? The same dou f by dou x. This is higher derivative. The same dou f by dou x. I've taken dou f by dou x. I can again differentiate it with respect to dou x. So this is, what is this? Remember, similar thing we did. Slope of slope.
Second derivative, yeah.
Second derivative. Right? How do I write it now? F. Look at that.
F square is
Look at this. Instead of y, there's an x.
fx square. Oh,
No.
fx.
Look at that carefully.
xx.
Ah. That's all. Right? It is a slope of slope with y constant. Right?
Yes.
So let us, I mean, you can give so many examples, no big deal. So let's say that some function of x, comma, y is, let's call that as z. So, I mean, z, that's which is f x, comma, y is equal to, say, x cubed plus x squared y cubed minus 2y squared. I'm just taking it from a book so that easy. So fx of x, comma, y. What is this? Dou f by dou x. Can someone help me? 3 into
X square
plus
y cube into 2x.
Y cube x. 2y
2x
cube
y cube
2 and 0.
minus 0.
right?
Yes.
0. I'm leaving it. Now, what is f xx?
6x
2y cube.
2y cube.
Brilliant. That's it. In fact, you will be surprised to know that this is an equation which is all the time used. Okay. Many times you, Josen, you will meet this all the time.
Yes, okay, sir.
So for example, velocity of blood flow, or I mean, of wave propagation, which you would see, okay, is a function of x, the position in the body or in the artery tree, and time. So you would notice, or you will, I will derive simple things later, because this becomes very important. The governing, we had differential equations, right? So this is ordinary differential equation is what we saw. You can have partial differential equations. I'm not going to teach this in this class, but I just wanted to tell you is equal to some a squared dou squared u by dou x squared. This is called wave equation. So you will have partial differential equation like this. One of the most famous equations in physiology, which decides every damn thing in physiology, okay, is what? Frequently it arises. What is the type of process you can think of in physiology? All the time it happens. Concentration changes, intercellular, extracellular, also from blood, many substances are taken out, so many things. What is the process? The number of processes. Simplest process. I mean, of course, osmosis. Physiology depends on one equation. Let me put it like this. What is it? Or what is the process? Diffusion. Anywhere and everywhere there is diffusion, right? So what is an equation which governs the diffusion, which we'll derive later, just to see how beautifully it comes out, is dou C by dou T. This is the concentration. So concentration variation, this is with respect to time. Obviously, concentration is a function of x and t. It can be x comma y comma t. That doesn't matter. It's equal to d into dou squared C by dou x squared. This is a very important equation in physiology. T is called as the diffusion constant. If that fellow is going to make trouble, you are going to be in trouble. Right? So this is what is called as a diffusion equation. So again, this is a partial differential equation. This is a partial differential equation. So this is called as the wave equation, because this is the equation. So when the heart pumps, you have a wave propagation, because it is not a constant. It pumps, and so pumping is with respect to time. So as the heart pumps, there's a wave that is generated from the heart, right? And that wave travels. So what is the equation that governs that wave traveling? Okay, is that equation which is given by dou squared u by dou x squared. So u governs, or u is, say, for example, it can be velocity and so on. Usually u is a displacement. But that is modified. I mean, I'm just saying that this is a wave equation. Of course, that is modified. Now, so the diffusion equation is how the concentration varies with respect to time. So these are what are called as partial differential equation. Essentially, Joseph, you will be solving this kind of equation. Don't worry, there are standard methods for doing it.
Yes.
Okay.
Yes.
Now, I'm going to give you an exercise which I want. There are a number of examples. We have seen this before. R is equal to C into some constant into L by R power 4. What is this equation? Eigenpoisson. Su. Eigenpoisson. Yeah. Now, what is R? R is the resistance. We had seen this before. We had done this calculation. So dou R by dou L is the variation of resistance with length, right? So what is that? C by R power 4. Dou R by dou small r. Small r is the radius. Clear? So what is this? Minus 4C.
4 by R raised to 5.
So when length increases, resistance increases. When radius increases, okay, radius increases, what happens? How? So minus dou R by dou R. So when the radius increases, it becomes negative, right? And hence there is a drop in resistance. Obviously, because it is R power 4 is down. When R keeps increasing, resistance keeps decreasing, and vice versa. Okay?
Yes, sir.
Right. I'm going to give you one example. In a class, I'm connecting a class. I'll talk to you later, tomorrow. Sorry, this is a phone call. So let us. So one of the interesting equations is I picked up all these things from various things where antibiotic. Okay, so that's given to a patient. So you are, say, let's say that you're putting IV. Okay, and so theta is the rate of input or supply. You're supplying at a rate theta. Okay, and V is the volume of the patient's blood. So, so as you give, obviously it's going to be metabolized. Okay, so the C, the concentration of the antibiotic in the blood, okay, is a function of theta and V, and is given by C naught e power minus 1 by V plus theta V to 1 minus, quite a complex equation, minus 1 by V. C naught is the initial concentration. which may be 0, or it, if you have taken it last time, there may be some value. Theta is, of course, a rate of, so suppose you have taken some oral, then it may be present. So I can do two things in this: dou C by dou theta and dou V by dou theta. Oh, sorry, dou C by dou V, not dou V by dou theta. Let me say dou C by. So what is dou C by dou theta? It is an increase, okay, in the concentration to the rate of supply. Okay, so in other words, when you increase the rate of supply, how much is the concentration increasing is given by dou C by dou theta. So what is dou C by dou V? The rate of increase of, I don't know, it may be minus. Dou C by dou V is, if I increase V, what is the change of concentration? Dou C by dou V. That's what it means. So you can calculate it and you can find out. So take this equation, see whether you can. If you're not able to differentiate it, don't worry, put it in ChatGPT. There are so many, this is so useful in a lot of things. So, for example, remember we had talked about urea. So, the concentration of urea in dialysis, rate at which is removed from the blood. Remember, we had three things: K by V, C naught, e power minus K by V into T. Remember this equation we had, first order differential equation we had. Now, the K is the rate of blood flow through the dialyzer. Through the dialyzer. Dialyzer. Right? Yeah. Now, this equation is very useful to you. If you are administering dialysis, then you want to know rate at which urea is removed. I want to know how much. I'm going to now increase the rate of blood flow through the dialyzer. I want to increase. Okay, and I want to calculate. This is a standard equation. You know, what is the advantage of knowing these equations? I'm saying. So, suppose you are a doctor. I mean, you are a doctor, of course. You are doing dialysis, and you want to now understand how the uh, DC, I mean, sorry, C is going to change when you change K. So what will you do in this equation?
Dou C by dou K.
Okay. Okay. So now how will you do this?
So C0 by V is constant.
So C0 by V is a constant.
K into e raised to minus K is chain rule.
Yeah. So I have dou by dou K into K into e power minus K by V into T. Right?
Yes.
Correct?
Yes.
So what is this?
So K into the chain rule. So first differentiate. So K into minus
K square by V e raised to minus K by
Wait,
KV by T.
So what is that you're going to differentiate now? First differentiate K. You're going to have two terms, right?
Yes. Yes.
So what are the two terms?
So first we differentiate K, then the first term would be e raised to minus KV by T.
Sorry, my pencil is not working. Just give me a second. Yes, e power minus K by V into T, then minus K into
e power minus k into
Yeah.
k e power minus kv by t. So k square
K by V.
k by v.
Right? So K by V into e power. Okay. So do that. Right?
Yes.
Do that part. Do that part. See whether. Okay. So these are some of the applications which you would see in partial differential equations. Right?
Yes.
Okay. So note that no differentiate this carefully. Okay. Differentiate that carefully. How will you differentiate it? So e power, say e power ax. How will you differentiate this?
A e raised to ax.
A e power ax.
Ax.
Right. So same way there. What is a in this case?
A would be t by v
Minus p by v.
minus t by v.
Minus
T by v.
minus t by v. Right. That's what will come down.
Yes.
So in this case, it is d by dk of e power minus k. Sorry, let me put it like this. Minus minus t by v,
Into k.
okay, into k. So what will come down?
Minus t by v.
Minus t by
Into
v will come down, right?
yes.
So how do you do this? There's nothing. So this is again chain rule, right? Again chain rule. That's all. Differentiate this with respect to this, and then again differentiate this guy. That is all.
Yes.
That's how you get this, right? Okay. Now, any questions, Dr. Shanti? Is it clear?
No, it isn't actually. I'll have to look at it once more. It is like, I think Josen and Arjun are at a different level. I was just thinking.
No problem, because they had say they are studying. So
Yeah.
I would suggest that you go through this once more, and we will then explain them. Okay, because these are very important things. Whenever you do research, some small mathematics is always useful. So this is actually simple. Go through it once more whenever you have time. Then what I'm going to do on Sunday, or even starting from next class, I'm going to go through every page of what I have done, so that one revision completely, and then I'm going to take problems and do more like this. Okay, so that would sort of, Joseph, I'm going to revise completely everything whatever I've done so far,
Yes, sir. Yes, sir.
so that every part of it, then I'm going to stop. Dr. Shanti can ask questions. We will stop there, and then uh, go ahead with that. Okay,
Yes, sir.
right. Uh, so there is one topic which I'm going to do is slightly difficult topic, okay, but is extensively used for solving this differential equation. That's called Laplace transform. Don't be very worried about this transform name and all that. So when we solve a differential equation, We solve this differential equation using MATLAB. We will continue to do it. But I want some insights into a differential equation. So, for example, a differential, a one compartment model or whatever it is, I can write down a differential equation, something like V into dc by dt plus some f into c of t is equal to some r, something like that. I can write down with an initial condition. Now, this differential equation, we solved it using numerical values and so on. So I can, so this is the differential equation, let's say. Ordinary differential equation. Now I can do some function, this is called transform, and convert it into a simple algebraic equation. Okay, and that is called Laplace transform with a L. Once I do this, I can solve this algebraic equation. So what is algebraic equation? It will be just s squared plus something like that. No, it will be very simple equation, algebraic equation. I have to solve that. Once I do this, I will come back with an inverse Laplace transform to get to the result. So this will give me the result. So it is very simple to do this. Only thing you require is what is this Laplace transform? Laplace transform has a huge theory and all that. We are not going to be worried about all this. I'm going to use MATLAB, ChatGPT, and a table like this. So there's a table which I will have. So for example, so the Laplace transform is written which is called as S, with a S. So the Laplace transform of a constant or something, is 1 by S. Laplace transform of t is 1 by S squared, and so on. So in other words, there is a formula which converts the time, what we call as time, to what is called as, this is called as a Laplace domain. Okay, so that takes me to an algebraic problem. Now, what I'm going to do is today I'm going to stop now. I will quickly run through this. It's very simple. One table is there. I'm going to do 4 or 5 problems so that you will understand it. I'm going to make it an algebraic equation, then solve it in the algebraic equation, and then come back and take an inverse of it, and I'm going to write it down. That's all. So in other words, if I have an equation like v dc by dt plus f of c of t is equal to r or something like that, I will convert this into a Laplace using this Laplace transform. I will convert it into an algebraic equation where c will be now function of s. So t becomes s here. Okay. Then I will solve, say for example, this equation will be something like this. V into S. Right now, don't ask me how you got it. I'm just giving you first an example. Into C of S is equal to V C initial condition plus R by S. Something like that it will come. So now I'm going to get what is C of S from this equation, and then do an inverse Laplace transform, inverse function of C of S will give me C of T. That's all. Okay. So it's a very nice tool to immediately look at the equations. How we are going to do it, I'll do that in the next class. Okay, simple. I'll take some simple equations and show you how this is done. You need not worry. Our MATLAB guy do it for you. It has a elegance, and immediately for one compartment model, all those things you can immediately look at it. It is extensively used in pharmacokinetics, PKPD, and so on, and used in physiology as well. Okay, so I'll stop here. Because something, have a look at it. Don't worry, because I'm going to go back and revise once or twice. You revise it, I'm going to revise it. So key concepts is what I'm interested in for interpretation. And I hope you appreciate that there are very simple applications for all these things.
Yes.
Right?
Yes.
Okay, because these kind of equations are always available. So then it becomes a simple interpretation of these equations. That's all. So we will do that again on Thursday, and we'll have a offline class on Sunday. We'll have a look at it. Okay. Yeah, we'll stop now.
Okay.
And we'll have a fresh class for. I'll finish this Laplace transform, and then I'll start revising completely. I'm going to put a full stop at that point.
Thank you.
Thank you.
Thank you, sir.
So this Sunday is 14th.
Thank you.
Pardon?
Sir, Karthike, Sunday is 14th.
Yeah.
பரவாயில்லையா?
Oh, வருஷப்பிறப்பா? I didn't. Oh, Sunday. Yeah. So all you guys are busy. Then give me some time. Other time. Oh, that's why Srinivasan said he's busy on 14th. Because 13th I have a meeting. I'm not available on 13th. Karthik, can you suggest sometime in the evening we can meet one day?
7 o'clock meet பண்ணலாம்.
எனக்கு ஒன்றும் பிரச்சனை இல்லை. Shanti, are you close by in Adair or?
I live in ECR. 7 to what time will that be?
7 to 9 or something, 9:30. அப்படி இல்லைன்னா அடுத்த வாரம் தான் வச்சுக்கணும். No problem. 21st.
Following Sunday. 21st.
Following Sunday. Okay. So I'll revise by that time. And I see when you use this MATLAB, it's better to be in person.
Yes, sir.
In person rather than sitting, it becomes very difficult to teach like this. Okay, we will see. If you, Dr. Shanti, if you give some other time, some other day, we'll be happy. We'll do that.
The provisional will present next Sunday, sir. 21st, sir.
Hello? Yeah?
Provisionally 21st வச்சுக்கலாம், sir.
Yeah. But what about 14th afternoon? Is it possible? Have good food and come?
Yeah, it
Alarm
should be okay.
2 to
14th
4.
afternoon should be okay.
14th,
Like even
2 to 4.
It should be okay with me.
Sure.
Yeah.
Sir, வீட்ல மேடம் கேட்டுக்கோங்க.
You have to ask madam. You ask madam and tell me.
What's that spine in your mail ID, Karthik?
எது?
Spine in mail ID ல ஒன்னு இருக்கே.
Yeah, I have no idea.
I understand.
We are spineless. No. I think 14 2 to 4 is fine, sir.
At 2 to 4? Yeah. Okay, Joseph,
Yes.
2 o'clock, then we'll meet.
Yes, sir.
Okay, sir.
Yes, sir.
Yes, sir.
Sunday afternoon. Yeah, great.
Sure.
Okay.
Thank you.
So anyway,
Bye.
we'll meet on Thursday.
Thank you.
Thank you, sir.
Thank you.
Bye.
Bye, sir.